Hi, welcome back to lecture 23 of AMA 221. And today I'll be talking about Taylor series. So you might remember last time we have used the geometric series formula to obtain some results. So the formula for geometric series is 1 over 1 minus x is summation n starts from 0 to infinity x to the n. Okay, where your x should be in between -1 to 1. So to obtain the power series for other similar functions, for example, 1 over 1 plus x, we saw that we can write this as 1 over 1 minus x, and then use the formula to get the series expansion for this new function, right? Which will be this, again, valid in between this interval. And also, we have seen how we can use the term by term derivative to get Taylor series expansion for a little bit different type of functions. For example, this one will get n x to the n minus 1, n starts from 1 to infinity. Again, valid in -1 to 1 interval. Okay. And similarly, how to use the integration term by term to get expression for Taylor series expression for ln1 plus x. This will give me ln1 plus x to be summation -1 to the n plus 1 x to the n over n. N goes from 1 to infinity, and x is valid in between -1 to 1. I have solved this problem, I believe, in the previous lecture. So this time my goal is to obtain power series for any quote-unquote nice function. So here, nice basically means a function that can be, differentiable infinitely many times, infinite often, in some interval about the point of approximation and the point of expansion. Basically the center of the series. Okay. So what are the sort of nice functions? Rational functions. Avoiding the zero denominator. This can be differentiated infinitely many often. Also like logarithmic functions, exponential functions, trigonometric function, etc. Okay. We also have seen that this is the series expansion for e to the x, and that is valid for all x. Okay. So Taylor series basically looks like this. Okay. Almost similar to the Taylor polynomial, but Taylor polynomial basically stops somewhere. Okay. So this is basically Taylor polynomial, where like Taylor polynomial of degree n would be of this form, where I have shown what will be exactly C0, what will be C1, and so on, what will be Cn. But for Taylor series, the main difference is it's a series, so it never stops. Okay, it goes on and on. In short, I can write this as Cn x minus c to the n, and it starts from 0 to infinity. Okay. And the same sort of interval of convergence is also valid here. So say R is the radius of convergence for this series. That means the expression, the series expansion is valid from C minus R to C plus R. Then to get, again, the values of C0, C1, C2, and so on, we will use the same kind of technique. So if we plug x equal to C in fx, then I'll get fc on the left hand side. So I'm like using this function, basically using this expression. So, and on the right, I'll have just C0. Everything else will be like 0. So I get C0 to be fc. Okay. And then differentiate fx term by term, then I'll get C1 plus 2C2 x minus c plus 3c2 x minus c square, and so on. Again, if I plug in x equal to c in this expression, I'll get left hand side is f prime c and right hand side will be c1 plus 0, and so on. All the other terms will be 0. So c1 is basically f prime c. Okay. Do the same process. Again, differentiate. I'll get 2c2 plus 3 times 2c2 x minus c, and rest of the terms. Again, plug in c in place of x, I'll get 2c2. So therefore, c2 will be f double prime c over 2. Do the process again. I'll get 3 times 2 times c2. And the next term will be like 4 times 3 times 2 x minus c plus so on. Plug in c, I'll get 3 times 2 times c2. So in other words, c2 will be, sorry, there is some, yeah, this should be c3. Okay, so I'll get c3 there, right? Should be c. So what I'll get c3 to be f triple prime c over 3 factorial, right? So in general, the coefficients will look like Cn is f nth derivative at c over n factorial, where n can be 0, 1, 2, and so on. Okay. So what we have done is exactly similar to find the coefficients for Taylor polynomial, as I already mentioned. And next, we need to see this theorem, which basically tells that if f has a power series expansion about a, then it must be of this form, fx to be this. So therefore, this is like unique, you can say. And this series is basically called Taylor series of f at a. Okay. And just like Maclaurin polynomial, for Maclaurin series, your a is basically 0. So when your a is 0, the series will look like this: f naught plus f prime 0 x plus f double prime 0 x squared over 2 factorial, and so on. And this series is called the Maclaurin series. Okay, cool. Now let's see some of the examples. So in this following example, I have two functions. One is e to the x, and another one is ln1 minus x. So remember, the Maclaurin series is given by this formula, n equal to 0 to infinity, f n derivative at 0 over n factorial x to the n. Okay. So fx is a function, doesn't matter how, like what order derivative you are doing, you'll get by the same function again and again. So f and derivative at 0 will be always e to the 0, which is 1. So the Maclaurin series for e to the x will be summation 1 over n factorial x to the n, and just from 0 to infinity. And if I write that down, then it'll be 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and so on. Okay, for the next function, I see f prime x will be 1 over 1 minus x. F double prime will be minus 1, 1 minus x to the minus 1, and then 1 more minus 1. For f triple prime, I'll get minus 1, and then 2. Okay, so okay, so there should be 1 minus 1 there. So yeah, f triple prime will be minus 1 times minus 2, 1 minus x to the minus 3, and there should be minus 1 square already there, and 1 more minus 1 because of the chain rule. Okay, this is not hard to evaluate, so you can figure it out later as well if you are a little bit confused right now. For fourth derivative, I'll get minus 1, minus 2, minus 3, 1 minus x to the minus 4, and then minus 1 to the third, and 1 more minus 1 like this. So in general, for nth derivative, I'll get minus 1, minus 2, so until minus n minus 1, right? I'm like trying to analyze the pattern involved. It'll be minus n, and then I'll have minus 1 to the n. Okay, so at 0, the nth derivative will be minus 1 to the n minus 1. I have collected all this minus together. There are n minus 1 of them. And then I find this 1 times 2 times so on till n minus 1, which is just n minus 1 factorial. And then I'll get 1 to the minus n, putting x equal to 0 there. And then at the end, there is minus 1 to the n. Okay. And this is basically minus 1 to the 2n minus 1, n minus 1 factorial. So minus 1 to the 2 minus 1. So this is odd. So therefore, I'll get minus n minus 1 factorial. Okay. So basically what's going on is just trying to analyze how the general form of derivative of log 1 minus x will look like. Okay, so Maclaurin series for ln 1 minus x will be, just try to write down all the terms. So square minus 1/3 x to the third minus 1/4 x to the fourth, and so on. So basically, in short, this is nothing but summation x to the n over n. There is one more minus there. So that's it. That's the answer. Okay. Next example is asking you to find Taylor series for ln x, but the point is the center is here, x equal to 2. So the Taylor series is of the form f n derivative at 2 x minus 2 to the n over n factorial, and n starts from 0 to infinity. Okay, cool. So fx is given ln x, f prime x will be 1 over x, double prime will be minus x to the minus 2, and it'll be 2 x to the minus 3. Then fourth derivative will be minus 2 times 3 times x to the minus 4, and so on. So if I evaluate all of this function and derivatives at 2, I'll get ln 2 and then half, then 2 over 2/3 minus no, then I'll get minus 1 over 2 square, and 2 over 2/3 minus 2 times 3 over 2/3 to the 4, sorry. So in general, the n derivative will look like minus 1 to the n plus 1, right? and then n minus 1 factorial x to the minus n. Okay, this is basically I got by analyzing this three, the pattern involved in this three, how the differentiation, higher differentiations kind of behaving. Okay. This is sometimes difficult to see right away, but with practice you will get it. But I need to evaluate the n derivative at q, so I'll get minus n to the n plus 1, n minus 1 factorial 2 to the minus n over n factorial, right? So which is nothing but minus 1 to the n plus 1, n minus 1, okay, just a second. Yeah. So yeah, so it will be minus 1 to the n minus 1, and then there will be n left there and 2 to the n there. Okay, cool. So the Taylor series will look like ln2 plus summation n equal to 1 to infinity minus 1 to the n plus 1 over n times 2 to the n x minus 2 to the n. Okay. And the question is where this Taylor series is valid. Okay. For that, you have to do ratio test. So you can evaluate it. I'm like writing down the result here. It will converge for x minus 2 to be less than 2 and diverge when modulus of x minus 2 is bigger than 2. Okay, and you need to, okay, just try to find space. But one thing you need to do is at the endpoints, I don't know what it will be. So if my x minus 2 is 2, then the series will be minus 1 to the n plus 1 over n, which is converging, right? Converges by alternative series test. And when x minus 2 is negative 2, then it will become minus 1 over n, which diverges. So therefore, this series expansion for ln x is valid when your when your x in between 0 to 4. Here 0 is not included, but 4 is. Okay, because at x equal to 4, I see that the series converges. And this is nothing but x equal to 0, right? So at 0, the series is diverging, so we should not include 0. Okay. So whenever you are writing the Taylor series, always you should mention that the Taylor series is valid where? What is the interval in which the Taylor series expansion will be representing to the actual function? Okay, cool. For the next section, try to recall that Taylor polynomial will look like this. This is already known to us, right? A full lecture on this. And we know that this is basically an approximation, so there should be a error involved in the expression, and the error basically satisfies this formula. Okay, we have also seen this, where c is in between x and a. Okay, this is the fact we have already seen. But so for Taylor series, our our remainder term, or like our error term, should tend to 0, right? Because this time I'm not dealing with a like n degree polynomial, I'm dealing with a series. So as n tends to infinity, my error should be smaller, 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 going to 0. Okay. So there is a theorem in regard to that. Suppose that the derivative of fx are all bounded on an interval I centered at x equal to a. So say in this interval a minus r to a plus r, I'm naming it by r. I'm naming it by I, sorry. So say in this interval, all the derivative of the function is bounded by a constant, okay? Then what happens is, then directly I can conclude that this Taylor series is valid for all x in I, okay? So in other words, the error will be like very small, okay? Why is that? Because see, I know that Rn x, this expression is less or equal to k x minus a to the n plus 1 over n plus 1 factorial, right? So remember, in place of k, I had n plus 1 derivative at c, something like this. This was the expression for Rn, right? But now I know that all the derivatives, all the higher power of derivative, when I consider higher order derivatives, these are bounded by k. So I just replace that n plus 1 derivative at c with k here. But then what happens? Then again, this is not hard to see that this is less or equal to k times r to the n plus 1 over n plus 1 factorial, right? Because x is coming from here, right? In this interval, x is from this interval. So x minus a will anyway be less than or equal to r. So I've just replaced that. And this tends to 0 as n tends to infinity. Because this quantity is basically fixed. This is a constant. But here n is tending to infinity. So therefore the error should be going to 0. Okay. So this is a subtle point, but I thought that I should mention it. Okay, so the next example is, asking you to basically verify that fx is equal to e to the x is valid everywhere. So if this Taylor series for e to the x is valid everywhere. So if I try to, estimate the nth derivative at c, it will be e to the c, right? We know it. And this is basically a constant k, say. So all the derivatives of e to the x at c is bounded by constant k. Okay, I'm just renaming this e to the c with k. Okay, just just to get in sync. Okay, now for fx to be sine x or cosine x, okay, so for fx to be sine x or cosine x, my nth derivative at c, modulus of that will be modulus of sine x or modulus of cosine x, right? And this is always bounded by 1 for all n, right? So both of these examples, I see that the nth derivative is bounded, and that doesn't depends on x, right? So for all x, these two bounds actually holds, okay? So therefore, the series expansion, which we have already kind of seen already, this three expression of in terms of Taylor series are valid for all x, right? So you can see I'm basically trying to apply the theorem, right? I see that all the derivatives are bounded, okay? And that bound doesn't depend on x. So therefore, for all x, the function is sort of behaving nicely, okay? The derivatives are bounded. Therefore, for all x, the Taylor series expansion will hold. Okay, so Let me now mention the methods for obtaining Taylor series, but most of the time, what happens is like in the problem, you will be asked to find Taylor series of a particular function. So these are the following methods you should approach those problems. The first one is brute force. I know the formula for Taylor series. I just compute the derivatives. I try to get the general form, and then I plug that all those derivatives into my formula. So the formula for Taylor series is just fx summation k equal to 0 to infinity f gets derivative at c times x minus c to the k over k factorial. Okay, so I just calculate all of this derivative and then plug into this formula. Okay, the second way is to substitute a known series. So if you need to find the Maclaurin series for xe to the x square, you can use the information that you already have. So I know that e to the x, I know the Taylor series expansion for e to the x, right? So I know that e to the x is just summation x to the n over n factorial. That is already something we have calculated. Okay, so basically I can use that. So if I replace e to the x with the x square, and I'll get x squared to the n over n factorial from this formula, right? N is going from 0 to infinity. And this expansion, we know that valid for all x. Okay, so therefore, I get the expansion without doing anything else. So I'll get x to the 2n plus 1 over n factorial summation n equal to 0 to infinity. And that is valid for all x. Okay, sweet. Or we could have get the Taylor series expansion for 1 over x as well at x equal to 2. So for this, what I need to do is I'll just forcefully add 2 and then subtract 2 from this. And if I take 1 over 2 factored out, then I'll get 1 over 1 plus x minus 2 over 2. Okay. Cool. But that is nothing but 1 over 2 times 1 over 1 minus x minus 2 over 2. Okay. I'm basically playing with the expression so that I get something which is known to me already. Okay, but this is nothing but like this I can think of as 1 over 1 minus x, right? And I know the series expansion for that, so I can use that. So if you just use the expansion we have already got and replace x with minus x over 2 over 2, x minus 2 over 2, I'll get minus x minus 2 over 2 to the n. Okay, but that series which I have already saved, this series, the geometry series actually, this series is valid when modulus of x is less than 1, right? So here also I should write modulus of minus x minus 2 over 2 should be less than 1. Okay, so what is this? If I try to rewrite, this is nothing but n equal to 0 to infinity minus 1 to the n over 2n plus 1 x minus 2 to the n, and that is valid for modulus of x minus 2 to be less than 2. Okay. Yeah, things are not difficult, just that you have to be a little bit careful. Okay, what about the next example? Here you have to find the Maclaurin series for sine hyperbolic x. So fx is sine hyperbolic x, derivative will be cosine hyperbolic x. We have already seen this. And then third derivative, second derivative will be again sine hyperbolic x. So if you put 0 for f and f prime, I'll get sine hyperbolic 0, which is 0, and then sine cosine hyperbolic 0, which is 1. And then again, 0 will be repeating, 0 and 1 will be repeating again and again. So the pattern is like 0, 1, 0, 1, and so on. Okay, so Maclaurin series for sine hyperbolic x will be x plus x to the third over 3 factorial, because all the other coefficients are 0 in between. And then x to the 5 over 5 factorial, x to the 7 over 7 factorial, uh, and so on. Okay, so from this I can get the Maclaurin series for cosine hyperbolic as well, because I know that derivative of sine hyperbolic x is cosine. So I can use that term by term derivative. So I'll get 1 plus x squared over 2 plus x to the 4 over 4 factorial, and so on. Okay. Or we can do something else. For sine hyperbolic x, I know that that expression is nothing but half minus half e to the x minus e to the minus x, right? And I know what is the series for e to the x, right? This is x to the n over n factorial, and this will be minus x to the n over n factorial. Okay, and both of these two series are defined for all x, right? So my final series for sine hyperbolic will be defined for all x as well. Okay, sweet. The next way to deal with the series is multiply or add or subtract known series. So if you see something like this in your paper, so here I'm given with the function sine x logarithm 1 plus x. I had to find the Maclaurin series, but up to the fourth power of x. Okay. Okay, so this is not like too bad to solve. So I know that sine x, I have already calculated that this is a series for that, and ln 1 plus x is given by this series. Both of two are already done, I guess, in the class. Okay. When we multiply this, that is nothing but multiplying both the series, okay, term by term, as simple as that. But the trick here is I have to find the first, I have to find till fourth order of x. Okay, so if I do the term by term multiplication, I'll get x times x minus x squared over 2 plus x to the third over 3, and so on. Okay, I'm not writing this all of this term because the next term will be at least x to the 4, right? But when you multiply x with x to the 4, you'll get x to the 5. That is not my concern. I need to find till x to the fourth power of x, right? According to the problem. So, and then I'll have x to the third over 3 factorial times x, and so on. The same reason here as well. The next term here will be like x squared at least. But when you multiply x to the third with x squared, you will get x to the 5. I do not need that. Now, if I multiply, I'll get x squared minus x to the 3 over 2 plus x to the 4 over 3 plus some terms. And from this, I'll get x to the 3, x to the 4 actually, over 6 and some more term. And if I try to like gather all of this, I'll get x squared minus x to the 3 over 2 plus x to the 4 over 6, and so on. Okay. And that is basically the expression of Taylor series expansion of this product. Yeah. Okay. For the other type where you have like division of a known series, so this time you have this function and you need to find the Maclaurin series up to x to the third power. Okay. Okay, so for this problem, again, we know what is the Taylor series expansion for sine. Let's write it down. Then I also know the, okay, but this time I do not have any other function to express in terms of Taylor series, because in the bottom or in denominator I have 1 minus x plus x square. So here I'll do the long division. I hope you know how to do the long division when you have the all of the expression as functions instead of numbers. Okay, so the first term is x, right? So I have to match this first term. So if I multiply this with x, then I'll get x minus x squared plus x to the third, right? And then I subtract, change the sign. This will cancel. I'll get x squared minus x to the 3 over 6 minus x to the 3, right? Um, uh, yeah, and then plus x to the 5 over 120. And there will be like more terms. Okay, so this is nothing but x squared minus 7 over 6 x to the third plus x to the 5 over 120. So again, I have to match this. So for that, I'll again multiply with x squared. So I'll get x squared minus x to the third plus x to the 4, I believe. And then again, change the sign, minus plus minus. So this will cancel out, right? And then if I add, it'll get minus 1 over 6 x to the third minus x to the 4 plus x to the 5 over 120, and rest of the terms, right? Okay, so again, I had to match this. For that, I'll multiply with minus 1 over 6 x to the third. Okay, so let me find a bit more space. Okay, now if I do the multiplication again, I'll get minus 1/6 x to the third plus 1/6 x to the 4 and minus 1/6 x to the 5. Again, change the sign like this. This will get cancelled. And I'll get minus 7 over 6 x to the 4 plus 7 over 10 x to the 5 plus so on. Okay. But so the next term there will be like something x to the 4 and so on. So I'm not bothered about that. So my expansion for of Taylor series will have first 3 terms as this, and rest of will be higher power of x. So that's it. For the next problem, I have to evaluate this integration, and I can approximate the integration, but then the error should be less than 0.001. Okay. So again, I'll use the Taylor series. So if I use the Taylor series, then e to the minus x squared, I have seen that that should be minus x squared to the n over n factorial, right? Okay. But then what I can do is I can basically simplify the expression by minus 1 to the n x to the 2n plus 4 over n factorial. dx, there should be dx as well. And n starts from 0 to infinity. And then I can change the sum and integration, the position of them. So I'll get this. Actually, what's at the end? Where n can be pulled out of the integration. So yeah, only this and then dx. So if I perform the integration, I'll get -1 to the n over n factorial, and then x to the 2n plus 5 over 2n plus 5 from 0 to 1. Okay. Again, I need some space. So this will be summation n equal to 0 to infinity -1 to the n factorial 2n plus 5, right? So I can write this as like 1 over 5. I'm writing the expression explicitly. Like, so 13 times minus. So if I calculate in the calculator, then this term is basically 0.001. So therefore, I'm like getting precise. What do I mean by that? So let me see. Write a page. Just a minute. Okay. So therefore, 0 to 1 x to the 4 e to the minus x squared dx lies between, so 1 over 5 minus 1 over 7 plus 1 over 9 times 2 factorial minus 1 over 11 times 3 factorial plus 1 over 13 times 4 factorial minus 1 over 15 times 5 factorial, which is 0.100196 and so on. And 1 over 5 minus 1 over 7 plus 1 over 9 times 2 factorial minus 1 this. Which is 0.100752. So basically, it'll lie between these two because this term is like 0.001. So the gap between these two is just 0.001. Okay. So therefore, and see, the first term is positive, second term is negative, again positive, negative. So like, the terms are like oscillating like this. So from this, I can guess that the actual exact value will be in between these two expressions. So basically you have to figure out till that term, which will be like less than the error permissible in the problem. Okay. Okay, cool. For the next problem, um, I'll skip this problem. I'll directly do this. So this problem I'll add in the notes, but I'll not solve it because it's like quite similar to what we were doing so far. Okay. same sort of logic goes on. Rather, I'll solve this one, which is you have to find the power series expansion for this. So remember, we have talked about partial fraction. Basically, you have to do the partial fraction here to, split this complicated thing into this too simple looking thing. And then you can take -2 factor out so that I get this plus 1 over 1 minus x. Okay, just rewriting so that I can apply the formula for geometric sum. So this and this cancels and gives you minus outside, and then x over 2 to the n plus minus x to the n summation n equal to 0 to infinity. Here, so 0 to infinity, right? But this series is valid for modulus of x minus 2 less than 1, right? Which implies modulus of x less than 2. And this is valid for minus x less than 1. So modulus of x less than 1. So if I combine these two, then I can take x to the n factor out, and then I'll get something like minus minus half to the n plus minus 1 to the n, and starts on 0 to infinity. But that is valid for the shorter of this, shorter between these two intervals, which is modulus of x is less than 1. Because this is valid for smaller region, this is valid for bigger region. So if I add these two, this two will be valid for, the region common between these two. So this is like common, right? Because what's this? This is like -1 to 1, right? And that is basically, -2 to 2. Okay. So therefore, for this common region, both the Caesar values. So therefore, when you combine these two by this addition, then that should be valid for the common part, okay, which is -1 to 1. Okay, so this is it. I guess now you can attempt the exam 2, and if you have any questions, you can ask me in the mail. Okay, thank you.